I'm Meir Toledano. I'm a data scientist at ANODOT, and I will speak today about real-time time series prediction, and especially on GPU. And first of all, sorry of my terrible French accent. I will do my best. So, let's talk a little bit about what is ANODOT, what we are going to do in ANODOT. ANODOT, we are doing anomaly detection on time series data that came from our client. We receive in real time up to millions of time series which are sampled up to minutes. So it's a huge quantity of data, and from this data we are detecting operational problems which call anomaly, and we are sending in real time anomalies to clients, and then they can take account of this and to fix the problem. So how it works? Mainly we are receiving metrics. This is the first point of the process. We are doing very complex machine learning and the basic idea of machine learning, we have this, is first to detect the anomaly on one time series to create unique anomaly. Then we are grouping them, and after we can give the service to the client. For instance, we can first visualize. The visualization of the metrics and the anomaly is important for the client. And the significant impact of machine learning is on the alert, the real-time alert. And then also there is possibility to investigate, to dig into, to understand why it's going on. For example, I put it on a simple example of, this is a real data from one of our clients. First, you can see that we have metrics that came from browsers, okay? These metrics, most of them are seasonal, which is also difficulties we have in ANODOT. And from this, in the blue, this is the data, and in the light blue, this is the production of our algorithm. In this case, the anomaly is what is outside the light blue, which is called the baseline. And here we can see the produced anomalies. And this is we are delivered to our client. We have a huge quantity of clients that are very like us, and we have Google, Microsoft, we have big ones, we have also German ones. We are working a lot with American clients, and here a short list of examples of clients. And today I promised you to discuss about prediction of time series, so let's talk about this. First, what I mean by what I want to speak today. First, in machine learning, there is always two parts. This is the modeling part, and then there is the inference part. And in time series modeling, this is also there is this dichotomy. This is always the two different parts. What I will not talk today, this is the first part. How from data to create a model. And to create a model, first you need to choose which model you want. This is what we call model identification. And the second part is how to estimate the parameter from the model. These two different parts I will not discuss today. And of course, I will not discuss politics, not discuss Trump about in Western world and something like this. But what I will talk today, this is the second part. This is how to create the inference. So I'm supposing we already have a model, and I'm supposing this is a good model. And the question is how to make prediction in the future. And for this we will use, so how I will do this? I first, for the example, I choose a toy model. A toy model is something very, very, very easy, very simple, and I call it toy model because in fact, all those techniques here, we can benchmark again, against a theory which is completely closed for this model since it's simple enough. And then for the prediction task, I will compare two different algorithms. The first one is the Monte Carlo, and the second one is what we call Fokker-Planck equation, and we will see what is going about. And then I will discuss about the implementation, both in CPU, both in GPU, and I will show you some results. So first, what I mean by prediction. Most of the time, prediction, it's depending of the horizon. Of course, I'm in the present. I want to make prediction in 1 week, 2 weeks, in X time in the future, which is called the horizon. And it's and of course the prediction is depending of this parameter, and it can be complex. Okay, here I plotted different distribution of the predicted value in the future, and it can be very different from one horizon to the second to another horizon. Most of the time, most use cases, we are interested only in the expectation. Okay, the boss just wants a value, a number. What will be the sales in 2 weeks? What will be my inventory in 1 month? This kind of question. So the answer is only a value. In terms of data science, this is only the expected value. This is the minimum things what we can do for time series prediction. A huge number of cases, we also are interested in the error of this prediction. Why? Because this is a measure of risk. Of course, if for instance we have a prediction of inventory, and this means that we need to buy. Okay, sorry, it's okay. And we are interested in the risk impacted by this prediction. For instance, if the prediction causes us to buy something, we are interested also to have the risk impacted by this value. But the most general, for some other cases, we are interested also in the tails of the distribution. For instance, you're working at PayPal. If you want to make prediction of fraud, we are not interested in the expectancy. We are interested in the worst cases we can have. For some companies, the tails here can be synonym of bankruptcy. So things, for instance, insurance company or banks, the loss or the maximum claims can be very problematic. So this is their main task in prediction. The general way is to predict the distribution in terms of data science. This is the prediction. So let's discuss now the toy model I choose. The toy model is very simple, don't worry. This is written in continuous world. So first, a small detail about notation. This is the small continuous increment in the time dt of the time series I want to model. And here, this is a notation for a noise. This is simply a Gaussian noise here. Okay, in this model, you have only two parameters, alpha and sigma. So we can also see as there is a small deterministic part and a random part. In fact, if there is no random part, there is no difficulty to make time series prediction. The difficulty in time series prediction is because there is noise, there is something that we don't know. So why I decided to choose to discuss about this model? First, for mathematicians, it's known, very complex name about the people who study them. For physicists, also, it's also known for physicists, but in other world, this is another name. This is mainly came from theory, from gas kinetic. For also bankers, it's also very known. This is a very known model from interest rate. So it is also known from bankers. And the question is for ANODOT, what is this model? We will see soon. I will not answer to this question now. So I promise you to discuss two different ways to make prediction. The first one is known by most of people that are working on time series modeling. This is the Monte Carlo way. The idea behind Monte Carlo is relatively easy. In fact, we have a model. We will write a discrete time model. We will simulate thousands of series based on this model. And from this, for each slice of time of trajectory we have simulated, this is our prediction. Okay? For each slice of time, we have only an approximation of the distribution. Don't worry, there will be a picture after. Okay, so first point, I said we will need to discretize our model. So the idea of discretizing is just by replacing the continuous difference to the discrete difference, and the increment of the Brownian motion is going to be just a random noise. So now, what is this model? We have this simple equation that we will put in a computer for simulation. And here, now, I can explain why I decided to choose to discuss about this model today. Because if you are a specialist of time series modeling, we recognize the very known autoregressive model, which is the simplest model we can start for time series modeling. Okay, every book on time series modeling is working about it. And here in ANODOT, we are working a lot with this model. So this was the opportunity to understand the mechanism of prediction in this model. So, as I said in phase 2, we will simulate thousands of trajectories based on this model. Here we can see we always starting from 0. Each trajectories we can see in different level of blue. It's a different trajectories. Here it's only plotted 10 different trajectories. As I say, our model is enough easy to have complex theory, so we can benchmark here in solid lines. This is the standard deviation of the theoretical prediction. Okay. So now we continue the procedure of prediction. We will choose an horizon. Here the horizon in the vertical dashed line, and then we will compute the histogram of all trajectories we already simulated. And this histogram we can see in blue, and this is an approximation of the prediction we want. And here in the black line, this is the theory. So we can see that we are close to the theory, but of course, since it's an approximation, it's very far. We are very far. This is the first drawback of the Monte Carlo simulation. It's only an approximation. If you want to be more precise, we need more trajectories, and then the problem in Monte Carlo, so we need far more trajectories to be a little bit more precise. So here is results we have. Okay, it's a bit slow. So anyway, so we will simulate all the different trajectories, and we are moving now the horizon, as we can see the evolution of the distribution. Okay, at the beginning the distribution is very, very sharp, which means that we are very sure about our prediction. Of course, this is an obvious deduction. The more we are far from the present, the less the prediction is good. Okay, so this is the idea behind Monte Carlo. I consider Monte Carlo as the state of the art of the time series prediction, especially because it is written in lots of different libraries, and especially in Facebook Prophet, for instance, that made a huge buzz several months ago. So it can be easily considered as a state of the art. Okay. Now let's discuss about something which is, in my opinion, less known. This is what I call the Fokker-Planck equation. Okay. The idea behind this is now we'll come back to the same continuous model we have, and from this we will jump to another field of mathematics which is called partial differential equation. Okay, don't worry about this, I will explain. So this is completely different from the normal time series world. Okay, from this equation we will solve it numerically, and that's enough. So there is no need for simulation, no need for histogram, no need for complex computation. This is the only point. This is doing just a little hard math, and then to write a very small code. So first, I'm almost sure that everyone knows what we are talking about, but maybe a small recall about it. So first, in partial differential equation, the unknown is a function, and it's function with at least two variables. Here in our problem, as I explained before, we are searching the distribution of the value. So it's minimum depending of the x, which is the value, and it's also depending of the horizon t. So this is our unknown in our problem. And what we call partial derivatives, it's the derivative according to each variable. It can be up to 2, for instance. So let's come back to our problem. As I said, this is our model. And here I will use clearly a magic trick. So you have to know that there is a jump between the time series modeling and the theory of partial differential equation, which is a very strong bridge. And this bridge can be huge in both ways, and there is a lot of different results what we can use. And today I will use only a small part and only in one direction. The small part is called the Fokker-Planck, also known as Kolmogorov forward for expert, and only in one way. So we have this equation that I discussed before, and I will transform it in this equation. And this is magic. This is clearly magic. I will explain why. First, it's absolutely not obvious that there is a link between these two objects. Okay? The second magic trick is here there is a random part, as we discussed before. And here there is no random. So in fact we transform something which is fundamentally random to something fundamentally deterministic. This is a huge trick that will improve the performance of the computation. Okay? And the second magic things, as I can say, in fact we are connecting two different things of mathematics. We will see how this very high mathematics will help us in the real world. So now let's talk about the numerical solution. Okay, so in our equation we have the unknown and those derivatives. We will just discretize them. So this value is transformed to an approximation, and we are transforming all these derivatives to the discrete derivatives. Nothing magic here. And the second order derivative, this is the formula. Nothing magic here. Now from this, we will re-inject those equations previously showed to this equation. Okay, and with doing a little math, we are rearranging all the stuff. And in discrete world, we have this equation with the constant A, B, C, which are depending on alpha and sigma, of course, and also of the discretized step, both on time and both on space. So as we can see, we have a very complex equation here, and this is very, very easy, and especially it's very easy to code in a computer. And this is what I put in a computer to create my prediction. Now, results. So first, we can see here, this is the solution of this simple equation. I just put the very simple equation and I compute the results. So this is the result. Here, this is the time prediction, the time horizon. Here, this is the X. This is the same view as previously seen in Monte Carlo. Here, the results. As we can see, we are in the beginning, so this is very tight. And here, this is only a zoom about the square here, because in fact the prediction is so high, so it is hard to see. So, what we have here, okay, so we can see, okay. So we have the prediction here that are what is going to the prediction according to the horizon. As we can see, the more the horizon is increasing and the larger is the distribution. And here, as we can see, we have directly access to the distribution. There is no need no need for more computation. The other thing that we can see easily, okay, so here in blue we have the numerical results, and in black we have the theoretical results. So we can see that in fact there is no difference, almost no difference. This techniques is inherently very, very precise. We don't need to simulate thousands of metrics, thousands of time series to be precise. It's automatically, it's free. Let's say it's free. Now, this has been the small part of mathematics, let's say, and let's come back to engineering and to discuss about how to code it. So I explained how to code it. This is a very simple equation, and this is numerical result we made here in ANODOT. And this is clearly the wow slide, okay? It was hard to believe in our labs that, that figures are good. So let's first discuss about the Monte Carlo. We made first, let's say that CPU is, of course, in C, C++. GPU is on NVIDIA. And this is the result, what we have in Monte Carlo. This is coherent with what Facebook Prophet, for instance, are saying. In fact, for computing their Monte Carlo simulation, they say that it takes few minutes. Okay, so here you have a result in seconds. This is more or less the same order of magnitude. By using hard math, as I explained, I just gain 2 orders of magnitude. So it is a huge result only with math. Okay. Then I decided that, okay, we have something very good. Let's push forward and to improve this implementation and I coded in GPU. And in GPU, this was a huge boost. It was a huge boost. We double check thousands of times how to do this. In fact, this is our result. This is 4,000 better than in CPU. Of course, in CPU, this is not a parallel implementation. In GPU, it's a massively parallel implementation, but it's not natural to code this method in the parallel way. Why? Because the number of threads here is depending of the data. So it's not and the number of expected thread is always high. Okay, in this example, it's a toy example, so 80 thread is not huge. In a real world example, it can be far higher. So it's not natural to code it in CPU. This method is natural to code in GPU. And with so our method, okay, in ANODOT is a boost of 5 orders of magnitude. So it is clearly huge. So I also put some comparison of price. As we can see, this is the price based on Amazon. As we can see that we transform something which is very, very expensive to something almost free. This is less than $1. Of course, it's not included the cost of I/O. So just in conclusion, that we see that I just presented you the continuous twin of very known model, which is the autoregressive model, and I explain you 2 different methodologies of computing prediction and how to do this. As we see that the Fokker-Planck way is far better, and according to our numerical result, this is 5 orders of magnitude better. So it's a huge improvement. This is how we do real-time prediction. Of course, with several seconds, it can be real-time prediction. This is what we do. So thank you for your attention.